part 2 of steam engines. Why did I do this in 2 parts? Well, honestly, because I thought I could better regulate it. I'm sure this is part 2. Oh. This is why you never load up your slides. Never load up your slides in advance. Part 2. Theoretically, this was going to be on the 18th of January. Theoretically. This week hasn't worked out as planned. But it's getting there. And that's a good thing. But it's kind of like the steam engine story. It gets there eventually. It takes time. It does. And I currently look like I'm having, I don't know. There's so much light coming in at the moment. So yeah, I look. I have never seen my skin look so unblemished and white. Usually there's bruises. Steam engines. Steam engines. Shameless book plug. I'm gonna do this. But no, let's start off with the Steeple engine. You might have noticed something here. This does not look like a good engine to try and fit inside a ship, does it? It really doesn't. It's a Steeple engine. It's kind of like the walking beam engine, the cross engine, all the crosshead engines, all the other systems we've seen. It's kind of tall. Now, the Steeple is sometimes considered just another version of the crosshead. Sometimes it's considered different. But basically, the Steeple is an obsession of David Napier, who is a Scottish shipbuilder. And, well, basically he wants to build something which is the most efficient you can build this type of engine. Without really thinking, in my mind, of the exact problems of fitting this engine onto a ship. And I have to admit, the amount of ships which must have had, and did have, strange things protruding from the decks and all sorts of angles going on, and hull shapes which are designed around the power plant, it really starts to remind me of the 1920s, 1930s aircraft, where basically you got the biggest engine you could, and then you built an airframe around it. And if you're sort of going, well, no, sure, there's aerodynamics and this and that. Look at the Grunham Wildcat, the Hellcat, the Bearcat. All those aircraft, all those pugnacious aircraft, and there are a few others, are basically large engines with an airframe and wings attached. And the most obvious example of that is, of course, the Vought Corsair, which is basically 2/3 engine. Well, the early ships were exactly the same. Luckily, if you're building a ship which is big and this way, and it's got to be fat and it's got to be tall, well, it's going to have deep draft, but you can also build it quite long, so you can make it quite proficient for carrying lots of stuff. But that's not... You can start to see why warship captains and admiralties are going, well, we really like steam power, but yeah, we're going to keep with the side lever engine, because that just doesn't look that great. That might present a whole new targeting profile. Just try and figure out how you're going to protect that from damage. You're going to have to build a sort of funnel structure with armor. It's going to have its own sort of armored conning tower around it. Now, then we have the Siamese, aka the double cylinder. And you might immediately notice that this is lower. It's not that low, if we consider how HMS Retribution has to be designed in 1844. It's not that low, but it's still slightly lower than the previous things, and the previous examples. It is based around 2 identical vertical engine cylinders arranged side by side. The piston rods are attached to a common T-shaped crosshead, so kind of similar to the Steeple and the crosshead there. The vertical arm of the crosshead extended down between two cylinders and was attached at the bottom to both the crankshaft connecting rod and to a guide block that slid between the vertical sides of the cylinders, enabling the assembly to maintain the correct path as it moved. This engine was developed and invented, really, by Joseph Maudslay. That's the son of Henry Maudslay, another famous British engineer. And he invented it after his oscillating engine, which I'll be getting to later. It, for some reason, failed to achieve the same widespread acceptance. I can't think why. It was used, though, because of its size, in a number of mid-century warships, in that sort of 1850s area. Including the first warship fitted with a screw propeller, HMS Rattler. Which, of course, is famous for what she gets involved in 1843. Well, not really 1843, but not long after that. And that is why we have it here rather than later, because I wanted to talk about the Rattler versus Alecto, because this has an impact. This, of course, is a paddle wheel vessel versus a propeller. Paddle wheel versus a propeller. This has an impact on what kind of engines you need to build. Think about it. If the paddle steamer had won, if the paddle wheeled ship had proved to be the most effective and the most powerful, well, that's going to change your shape and form of your engines, isn't it? It's going to change what you need, because if you consider for a propeller, you want to send the power down the ship from where you'll have your engines, which will presumably be roughly amidships, to a point at the end where they will turn something that way. So they have to be mounted so they are turning something this way. Otherwise, you're going to need gearing and pivots and all sorts of things, which are doable, but they're complicated. And one of the interesting questions I've already had on various parts of the series this year was, well, why didn't they just have a folding propeller? Why haul the propeller up and the shaft up? Because they hadn't developed the folding propeller. It might seem really simple to us today, looking back. But it takes time to develop not only the necessary idea of folding the propeller, when you can just simply haul it up, but, well, that's actually more difficult, but it seems more straightforward, but also the need to do it, because, again, it comes to that critical cultural mass of knowledge, that cultural knowledge. If you do not have enough propellers in service, there aren't going to be enough people thinking about it to actually start thinking of different ways of how to deal with this problem. If you have only a dozen propeller warships, or propeller ships going around in the world, how many people are going to be really thinking about them? Let's put it another way. Think about the modern world we live in today. And think about car modification. Now, this isn't necessarily as big a thing in Europe and Britain as it is in America. I know, because I have relatives over in America and Canada, and I drive my own cars in the UK, but I've also driven cars in Europe. Modification isn't really as big a thing. But if you were looking for modification kits, would it be easier to find them for something which is produced by Ford or by Subaru, or for something which is produced by Ferrari? Probably not. Probably easier to find it for the cars which are more mass produced, for the Toyotas. Why? Because there are more of them. So if someone's going to be thinking about producing a modification kit, they're going to be thinking about something which they can market. There is no point producing something for which there are going to be maybe 200 cars produced worldwide, and there might be 5 or 6 of those people who actually want to modify their cars. There's no point producing a modification kit for that. If they're going to do it, they're going to have the money and they're going to pay for it to be a custom job. They're not going to need to get a generic kit or think about a generic kit. But if you're talking about something which might have 200,000 versions constructed, then suddenly the percentages of people who might want it modified goes higher, their likely bank balance goes lower, and they will want the kits. So it becomes economically viable to produce the modification kits. It's the same with ship and engines. If most of your ships coming on this period are paddle steamers, are paddled vessels, this makes sense of a lot of these engines I've been discussing. It makes sense of them because when they go up, well, there's already a large paddle wheel there. Already something you don't want to get hit. It's also a problem for warships as it breaks up their ability to fire a broadside, which at this point is still the critical thing. And it presents something very vulnerable on your broadside. But it is the reliable, consistent methodology being used. One of the interesting things that I've often had discussed with people is if paddle steamers, if Alecto had won this rather than a Rattler, there is an idea in my mind that you are more likely to get turrets developed earlier. Why? Because you have a blind spot on your broadside, which has always been traditionally covered, and now you need to think of a way of fixing that. The other option is you get ships which are far bigger, far higher, so they can have a line of guns over their paddle wheel. Maybe even internal paddle wheels like you had appeared during the Civil War. That is the US Civil War. So there are lots of different variations of history which come about if Alecto wins this over Rattler. But Rattler wins. And so that means the propeller becomes the key methodology. It's the thing the Royal Navy decides to focus in on. And once the Royal Navy's made that decision, again, this is one of the things you have with cultural memory. Once the major power, the major maritime power makes a decision, most of the other nations are going to follow it. Because their view is going to be quite simple. We're putting in less money into the Navy than the Royal Navy is. We're putting in less effort than the Royal Navy is. And the Royal Navy are the Royal Navy. If they've decided to go this, and they've decided the balance of evidence leads this way, they're probably right. We can either invest money and spend our money replicating those tests and trying to figure it out for ourselves and probably come to the same conclusion, or we can just go the way they're going. That's the way it happens. So, this is the story of the Rattler. Now, she was built in Sheerness Dockyard. Originally ordered as a paddle-wheeled 4-gun steam vessel, that's steam vessel second class, she actually became a 9-gun steam screw sloop. Her order is changed in February 1842 from the Royal Dockyard Sheerness, so she's built by the Royal Navy in one of their own dockyards. And William Siddons is called to redesign the ship because, frankly, there's no one else they want to trust, and he's the surveyor of the Navy at that point, and he's very capable. She was the 5th ship to be named the Rattler, rather appropriately. Named for the snake, not for the fact the engine rattled away, but, you know, hey-ho. And her engine was a Maudsley, recognise that name for earlier, Sun and Field 4-cylinder vertical single expansion steam engine with double cylinders of 40.25 inches with a working stroke of 48 inches, rated at 200, please note that, 200 horsepower. That's a massive amount. I mean, nominal 200 horsepower. Nominal, please note. She had her copper bottom, which was done for her at Woolwich Dockyard, and her armament consisted of either a single 8-inch loading smoothbore, or a single 68 pounder on a pivot mount, and 8 Blomfield 32 pounder solid shotguns on broadside trucks. Cost of the machinery and fitting out came in at somewhere in the region of £27,000. Probably just shy of that. So for £27,000, they built a ship with a barkentine stale plan and the ability to use a propeller to get her going along. After this historic test, she then spent most of her life on the west coast of Africa and East Indies Station, and she did a lot of work there. She would eventually be paid off at Woolwich in 1856 and broken up at Woolwich in 1856. So she doesn't serve for a massively long time, but if you consider launched 1843, in this period, 13 years, there's a lot of technology that develops in those 13 years. And then we have the direct acting engines. Now, there are two definitions of this. Two, and I'm going to expand the plan so you can see it a bit more. The earlier definition, the term direct acting, applied to any type of engine other than a beam. So it could be a walking beam, side lead, or grasshopper engine. Later on, it's used as a term for engines that apply power directly to the crankshaft via the piston rod and or connecting rod. This I'm primarily talking about is the later version. A direct acting engine could be readily adapted to power either paddle wheels or a propeller. This made it very useful, as well as offering lower power direct acting engines that had the advantage of being smaller and weighing considerably less than beam or side lever engines, and taking up less space in a hull. The Royal Navy, after doing some testing, found that an average direct acting engine weighed 40% less, required an engine room only 2/3 the size of that of a side lever of equivalent power. However, they had a disadvantage, as such engines were more prone to wear and tear and thus required more maintenance and tended to require more crew. In simple terms, there is no easy win. There is no easy, this has got to be the solution, this is the answer. Just not the way it is. Just not the way it is. Then we have the oscillating engine, and by the way, this is the paddle wheel engines of HMS Black Eagle. Yes, the Royal Navy had a ship called Black Eagle, originally called Firebrand, rebuilt as Black Eagle, and employed as an Admiralty steam yacht. A good-looking ship, and let's be honest, Firebrand or Black Eagle are both very cool names to have. Now, the idea of an oscillating engine is it's a direct acting engine that's designed to achieve further reductions in the engine size and weight. And with oscillating engines, they have their piston rods directly connected to the crankshaft, dispensing the need of connecting rods entirely. To achieve this, the engine cylinders were not immobile, they moved. They were secured in the middle by trunnions that let the cylinders themselves pivot back and forth as the crankshaft rotated. Hence the term oscillating. They oscillate because the pistons themselves move. If you are currently thinking this sounds like a health and safety nightmare, then I would remind you that most of the health and safety regulation which we today take for granted or spend our lives railing against as government red tape didn't exist. I'm not going to say this to suggest that such a thing is necessary, but they literally fitted this in ships, okay? In ships which move and roll from side to side in water, they had engines where the actual cylinders move. Okay? Just go through the mental geometry of what that could entail, and then be surprised that these are not in service for a massively long time. steam was supplied and exhausted through the trunnions. The oscillating motion of the cylinder was usually used to line up ports in the trunnions to direct the steam feed and exhaust to the cylinder at the correct times. However, separate valves were often provided, controlled by the oscillating motion. This let the timing be varied by enable expansive working, so there are some advantages. But whilst Joseph Maudsley builds it in 1827 first, John Penn is the person who really sort of perfects it. The fact that these engines remained popular as a marine engine for much of the 19th century, again, demonstrates to me people's love of efficiency over what I would call logical health and safety in trying not to kill their own crew. It happens. Trunk engines. Ah, yes, the trunk. Now, this is another type of direct acting engine, and originally developed as a means of reducing the engine's height whilst retaining a long stroke. Instead of having the stroke being up and down, they thought, let's go and make it go like that, because this is going to give you power. Now, I'm looking forward to seeing an original trunk engine of the gunboat type, because which is held in Western Australian Museum in Fremantle. I'm hoping to get to see that during the trip to Australia this year, which, if everything works out fine, will be the history team's trip to Australia. But more of that will be announced later. Not in this video, but later on in this month. Trunk engines did not work well with high boiler pressures in the late 19th century. And so builders started to abandon them because they had this habit of, how do I put this politely, jamming or exploding. That was really your choice with the higher boiler pressures. However, and I will say this in their defense, that is with the metallurgy available in the 1870s. And this is something else we should consider when looking through these engines. No, just no. But, you know, some of these engine systems, we automatically think, oh, well, they were replaced by the expansion engines, so obviously they're not as good. They weren't as good under the ideas and abilities of the times in terms of how we could design metal, etc. And how we could build boilers and the trunk casings, etc. But it is worth revisiting ideas every now and again. And one of the interesting things, I think, with trunk engines is that I have seen recently a lot of discussion of them, because they could be made to be very, very efficient. The trouble was, you could only keep them efficient at low boiler pressure, and that wasn't useful for what was being done. Change it around, it could be interesting. It could also still blow up. We don't know. We'd have to do a lot of computer probably a lot of computer simulations to work it out, and even then, if we got one working, we'd have to actually build it and run it and test it and see what happened to it. Now, I'm game for that, but apparently Rolls-Royce and most normal engine manufacturers aren't. Which I find sad, but I might start a letter writing campaign on it. Then we have the vibrating lever, or half-trunk engine, which was conceived by John Ericsson because he needed a small, low-profile engine, like the trunk engine, to power monitors. The trunk engine was unsuitable for monitors because the preponderance of weight was on the side of the engine that contained the cylinder and the trunk. You can't compensate for that with ballast on small monitor ships. They don't have the space. Sir Ericsson resolved this by placing two horizontal cylinders back to back in the middle of the engine working two vibrating levers, one on each side, which, by means of shafts and additional levers, rotated a centrally located crankshaft. Oh joy, this does not sound complicated at all for a monitor. Brilliant. They were only ever used on American and Swedish warships. However, many merchant vessels also tried them out. They were soon supplanted by other engines, and I cannot think why, considering the sheer amount of maintenance such a configuration must have required. The sheer amount of maintenance. Then we have the back-acting, otherwise known as the return connecting rod engine. Isn't that cute? And this is the example of the engine aboard HMS Agincourt, built in 1865. Now, it's arguable and probably correct. This is actually a modified Steeple engine, which is laid horizontally across the keel of the ship rather than standing vertically above it. Basically, if you think about all those earlier engines which were high and went high, they were not good for warships. So a lot of people went, well, that engine works, but just doesn't work in that configuration for a warship. So let's see if we can't figure out a way to make it work for a warship. Instead of the triangular crosshead assembly found in a Steeple engine, the back-acting engine generally used a set of two or more elongated parallel piston rods terminating a crosshead to perform the same function. The term back-acting derives from the fact that the connecting rod returns from the side of the engine opposite the engine cylinder to rotate a centrally located crankshaft. Again, if you're thinking about how complicated that can be, well, I would say, for an idea of its complexity, have a look at a Rankle engine, and that might give you a good idea. They were still quite popular despite this complexity. There is only one known surviving back-acting engine, that of the formerly USS Ranger, currently then what became the TV Emery Rice, that's preserved as a centerpiece in the American Merchant Marine Museum. It's worth going and having a look at that, because the whole point of this breaking steam engines up into two parts and discussing them like this is because I want it to be sort of realized just how varied the engines were. The idea that they quickly worked out a marine steam engine, no. As said, the boilers, and as we already discussed, some engines did not work well with high pressure boilers. Some engines don't work well with low pressure boilers. And by the way, that's high or low pressure by the standards of the 19th century, not by the standards of the 20th century, which we've already discussed in the first part. And then we have the vertical engine. So, now, broadly speaking, I'm going to be talking about expansion engines as we go on, but these are the first sort of, they're all grouped in the vertical level of them making them vertical. Making it go up. Now, this is a hammer engine. Oh. That one allows you to really lay your hammer down. And this is the vertical trip expansion engine of the USS Wisconsin, the BB-9. Now, the vertical engines are a product of their age. As ships grow in size, as they get bigger, especially as you get steel ships, which can be bigger, that problem which I've talked about the whole way through of having an engine which goes high up and therefore pokes out your deck becomes less and less of a problem because you have more and more space below deck. So now, Your problem becomes cramming in as much as you can lengthwise, rather than height-wise. So the vertical engines return. So all the things I've been talking about with the previous engines, which were their problems because they stuck above the deck and were terrible because of that, and dangerous because of that for warships. As warship technology changes, the engine which suits them changes, and so we have the vertical engines come back. Now, in this type of engine, the cylinders are located directly above the crankshaft, with the piston rod connecting rod assemblies forming more or less a straight line between the two. It's similar to what the form of a modern internal combustion engine, although there is of course the difference being that the steam engine is double acting, whereas internal combustion engines generate power only in the downward stroke. They're single acting, for want of a better phraseology in my mind at the moment. They are, how do I put this politely? They become a group, and slowly once you have this engine formed, then it becomes a variation on them. And it starts out with single cylinder, simple expansion engines. Okay, so they have one cylinder. But then you get compound, two cylinders, because it's compound action. Then you have triple, and then you have multiple expansion, which can be quadruple and even quintuple, I think, in one vessel, just for the joy of it. And basically this refers to how many cylinders you put that steam through. And you can only do that with higher pressure steam, because if you have a low pressure boiler, it isn't not going to push more than one single expansion. But the moment you have high enough pressure, well, the steam which comes out of the first chamber can then work in the second chamber, can then work in the third chamber. And you get something which is sort of like this. Sort of like this. This is a compound steam engine. And if you want to see a good example of that and some pictures inside of it, please go to the Sackville video on this channel. I did a lot of sticking the camera inside the engine as much as I could. And this is what I mean by the fact that you need the high pressure, because high pressure comes in here, pushes this on up, and then that steam escapes into the second chamber, which it then works on, and then it escapes into the third, which it then works on. And this is it. This is how it generates power. This is how it makes it work. And how it also gets it as much power as it does out of the steam. Because every single chamber you're adding on gives you another layer to get more and more of that power, to make it more and more efficient. This is why triple expansion engines are quite so efficient. But also, they are the product of literally many, many years of development. Broadly speaking, 100 years of development. When you're looking around in World War II and you are thinking about whether we put in a turbine or a triple expansion engine, the triple expansion engine, you can take it right the way back to the Charlotte Dundas. There is not much difference going on there in principle. You can draw this as your starting point, all the way up to getting to through these, to these, through these. Thank God they didn't try and make them oscillating. To this. So they have, it's kind of like today with the internal combustion engine. We have been building them for so long. We are now getting very, very efficient at drawing every bit of energy we can from their ability to produce power. Every bit of energy we can. Which is one of the reasons why those hybrids, which are diesel electric or petrol electric, work so well. when you put in this little diesel engine in, and with a huge battery, and the idea is you can charge it or you can fill it up with petrol and diesel, and if it runs out of electricity, it flicks on that engine, or if it reaches a point where it needs more power than the battery can produce, it flicks on the engine. That little engine can provide enough power for that. And everything can be focused around the most efficient way to generate that power. We can do that because of the 100+ years of development we have going into the internal combustion engine. The reason we were able to build the ships we were able to build in World War II, which was so efficient using this technology, was because it had been around for eons by that time. Yes, the turbine, which is the next engine we're talking about, is an improvement. A steam turbine is a very, very powerful tool. It does allow you to get even more power out of that steam. But it was still relatively new and relatively going through the process of being refined and improved. This technology had long passed away from the field of the innovators to the efficientators, which again, if you've watched the first part of this video series, you will know what I'm talking about. Innovator engineers are the ones who come in and solve problems and come up with great ideas and all these things. Efficientators are engineers, and this might be a King's University term, it might not, it might be a regular engineering term, are engineers who come in after the solution has been found and make everything work a lot better, slowly, by making incremental improvements. Often they are two different people. It's very rare you can find one engineer who's both encapsulated in one person. Because one is often a lot more patience and administration. The other one is charging through patience and administration to solve the problem. And then we have turbines come along. Well, this is an AEG one from 1905. And this is Turbina in 1897 at Spearhead Review. Turbines are a different kettle of fish in very, very simple ways. Now, I just want to check to my notes and remember something. Please note that a triple expansion engine is defined by the number of stages, i.e. this is 3 stages. The Titanic, for example, had 4-cylinder triple expansion engines. So it's defined by the number of stages the steam goes through, not the number of cylinders. Which is why you could have a 4-stage expansion engine, quadruple, or as it's called here, multiple expansion engine. But you can also have a 3-stage quadruple cylinder engine. Just to make life slightly more complicated. And, of course, if we remember correctly, the Liberty ships were all powered by triple expansion engines. There is a reason for that. Because we have this idea that the US ability to produce stuff was infinite in World War II. It wasn't. They couldn't produce enough turbines to power Liberty ships as well as all the warships they were building, because they wanted the warships to be turbine powered. But they still had all this production facility available for these engines, for triple expansion engines. And they were reliable, and they were exactly what they needed for a merchant ship. So they used these. They were a very refined, very capable piece of technology. It makes sense. Turbines. Now, one of the interesting things is if we go back to the ALU file from the very first slide of the first part of this series, go all the way back, all the way back to here. That's probably more accurately described as a steam turbine than a steam engine. It's certainly closer in principle to what steam turbines look like today. Steam turbines can look like today. Because a steam turbine can be designed in one of two ways. It can be designed as, for want of a better phrase, a whole set of fans where the steam goes through and that turns them, or they can be a whole set of systems which, well, nozzles, which where you have, well, you can have it so that the nozzles shoot steam onto the fans, or you can have it so that nozzles come from the fans and turn the turbine. There are different designs depending on what you want from your turbine, and some turbines even use a combination of the two, just to be complicated. Turbines don't start with Parsons. In fact, you can go back a long time and find various people working on turbines, as I just pointed out. The thing about Parson is that he makes it work. You know, James Watt had in 1775 produced what we would call a reaction turbine and put it to work in Soho. Yeah, Soho. That space in London which is Soho. Charles Parsons, well, in 1884 he makes one and he connects it to a dynamo. The thing about Parsons' turbine, the really important thing, is it's replicable and it works. And by what I mean by replicable is that it's able to be built using the metallurgy and everything else at a time at a consistent level. You're not making a special thing that you can basically do as a one-off. You can actually build it using the facilities available at the time, the infrastructure, the industry, the collective memory and knowledge at the time, and actually make it reliable, make it work. It's still very, very high-tech engineering. It is massively high-tech engineering for its time, but it's able to be done. Within Parsons' lifetime, the generating capacity of a turbine was scaled up 10,000 times. Now, his first turbine was 7.5 kilowatts, its power output. He very rapidly got it up to 50,000 kilowatts and then got it even higher. But of course, in terms of it powering engines, it's usually a direct drive system. As we'd think about it in terms of engines, with it being directly connected or occasionally through gearing as time goes on, connected, and that's why we get the geared steam turbine sets, which are connected to the shaft that powers the screw, the propeller. Now this again causes a revolution in ship design. Why? Because if you were designing something which was supposed to fit this in its forms, you've got a lot of space vertically. Again, this shrinks down the space. And it becomes even more important as you are seeking to build ships with better and better protection. Because if you've got an engine which takes up less space, it requires less armor. And that matters, because armor is expensive. We might say steel and air is cheap in terms of ship design, and that's true. But armor has and always will be more expensive than steel, even though it is a form of steel. But what really makes this all possible are the boilers. Yes. High pressure and the power of the steam coming through is what makes a turbine actually work. If you had the original versions of boilers, if you go back to the boilers you could get in the 1800s, you could probably make one of these triple expansion engines work off it. Or rather, if you had enough of them, you could possibly make it work. You could never really make one of them work with a turbine. Now, the low pressure boiler, which is the bottom right as you're looking at it, this one. And then you have a high pressure boiler, top right. Then we have the double-ended, which is top left. And we have the low type of high pressure boiler, bottom left. Okay, so this is where it gets really fun. There are all these different boiler types. There are even more boiler types than I've got listed here. Boiler types are important because the more advanced boiler you get, the better, but also the more complications you get. A double-ended boiler, it can sound really sensible. Oh yeah, we've got multiple sources of heat. We're really ramping up the heat. If something goes wrong in that boiler, you got a lot of problems. Because it's very difficult to make it accessible. High pressure, standard boiler, still not that great, but you can do more things. You can tend to design it so it is accessible at certain points, although it is still going to be pretty complicated. If you might notice, the chamber gets bigger as you go down the pressures. That makes things easier to access and maintain and repair, so it makes it less likely you're going to need to do an entire boiler reinstall. But all these boilers matter because you get efficiency from two sources in a steam engine. You get efficiency from your ability to draw energy from the steam, but you also get efficiency in your ability to convert your source of energy into steam. So you need the boiler to be the maximum efficiency possible to get the most steam out of that heat source, and you need the engine to be the most efficient it can be to get the maximum energy out of that steam in order for it to work. In order for you to be able to do what you need to do and get the power to move. All this takes time to develop. Again, there is a reason why steam engines are different, why different nations have different variations on what is their high pressure steam in World War II. Because it's when you decide to change your boilers over, it's when you pick up off the energy tech tree, but also when you decide to pick off the maintenance tech tree. What are you looking for in an engine? Are you looking for the very best, fastest, most powerful engine possible? Or are you looking for something which is more on the reliability scale that's going to allow you to operate all around the world with minimal maintenance or relatively minimal maintenance? It's going to affect which boiler you're going to pick, and that's going to affect which engine is probably best to run with it. It's a summary. Now, summary would be quicker, but I've had a pizza just arrived, so I'm hungry. And the main point of summary for this and for engines is that it's time. We like to believe that we have all the answers today. We don't. We like to believe we're very advanced. We aren't. In 200, 300 years, people look back on us and go, I can't believe those historians were just recording in this sort of basic 3D format, where you can see them presented in a 2D way, when they could have had a multispectral camera and they could have been standing in a hologram in your room teaching you individually. The engines today are probably not the engines of tomorrow. But it takes time to get there. For every innovation where you push forward into a new technology, there'll be far more efficienting and getting it effective and making it more viable and more effective. What these engine videos have mainly been about are the transition from steam power into eventually turbine power. And I haven't gone much beyond turbine power and into diesel engines, etc., because they're coming up later on. But the point is, this all comes about because of a very, very long-term development. It comes about because people need power to maximize human power in the mines. That's where the engines start off. And then they start wanting to move goods. And then eventually to get on from goods on shore to goods in a canal. And then from goods in a canal to goods at sea. But all these points of view, you need to develop not just the ability to do it, but the infrastructure to do it. There is no point sending a coal-fired ship from transatlantic if you can't find coal on the other side. Now, that might sound really obvious. Of course you can find coal in America. You can, but is there coal going to be in the port, able to be used and able to be loaded onto the ships? Is it going to be in a form that's viable? Because if it isn't, you're in trouble. In simple terms, it's not easy. And it takes time. And technology is more like that than we like to think. We like to see technology as this constant line going up to greatness, and it isn't. And what's even more cases with some of these technologies is if they are left, is if people look at them and go, well, hang on, that hasn't really worked out for us. That's not really working that well. And they park it to one side. Then it might well regress, so we might forget how to do it at that level and might go back even further. So when we look at it again, we go, well, we can't use that technology because we can only do this with it. And yet, in reality, if we carried on developing that technology, it might have been the perfect solution for the problem we have now. Which is why today engineers spend a lot of time looking over history documents and looking over old patents and looking over old proposed solutions for problems, because the solution might not have been right at that time, but it might be the solution for us today. Reinventing the wheel is slightly more useful in terms of reimagining what were the other potential solutions instead of a wheel than we might think. Anyway, I hope you enjoyed this video. I hope you enjoyed these two-part videos. And I hope you're going to join me for Patron 71. That's going to be this evening. I know it says Wednesday the 18th of January behind me, but it's actually the 19th. Right, I'm going to go off and have my lunch. Thank you very much for watching. I hope you enjoyed. And, well, with engineering, I always said, what other technologies do you think sort of have got missed in terms of we've moved past them because the metallurgy and the systems weren't available? But I'd like to hear your ideas about what technologies you think we've skipped past because they didn't have the infrastructure available when they were being looked at, and so we moved on to other things which were more easy or more available infrastructure when, frankly, they would have been better solutions. But for an idea, I would say Brunel's view on railways. He wanted wide gauge. He wanted those gauges to be wider because he thought that would allow you to build bigger, faster, better trains. And he's right. But standard gauge wins out because it's more easy to assemble the existing infrastructure. And so the Act of Parliament goes through. But I do sometimes look back and look at our infrastructure in the UK and around the world and wonder, what would have happened if Brunel had won that argument? How would the world be different if railways were all on wide gauge? They wouldn't be able to take corners as quickly, but honestly, if we consider the trains, they'd probably be far more useful and far more efficient than we have today. Thank you very much for watching, and hope you enjoyed.